last time we were doing a problem on repeated measures, the thermometer problem. We are going to continue the same problem. We did a two-tailed test. We found the test statistic. I did all that work so that in case the homework system wants you to do it, you know how, hopefully, which is why we have the formula. But our principle is about understanding the concept and can you input things properly and make use of technology when it's available. I showed you how we can get the mean, standard deviation, etc. using the calculator. I showed you how to find the p-value, which was painful value. Sophie asked me, well, how do we get to inverse t if we don't have the calculator? We need this table. I always just put it on the exam, you don't have to print it, which we looking hippie. I don't know if it really helps, but in my mind it does. The test that we did is a two-tailed test. So in the table, on two sides, degrees of freedom was 7, and over alpha was 0.05. Yes, that is the number. So if your calculator does not have inverse t, you should use the table. Good. Now, we have an easier way of doing things. You know, we have the technology, we put it in good use. So there is some give or take always. Certain things you can get it directly from the calculator, and some bits you can't. And of course, to infer something and answer a problem properly, you can't simply use the calculator. It's going to give you numbers, but you are the one who's going to make the decision and think properly. So last time we had temperatures from the first trial. We went for a second trial just to make sure that our thermometer is working properly. And in list 3, what do we have? Let's see if you remember. Louder, sir, if you are correct.
Yes, the difference.
The difference between L1 and L2. In this problem, it doesn't matter whether you do L1 minus L2 or L2 minus L1. But within subject design, you should always be mindful of how you define the difference. Otherwise, your conclusion is going to be entirely wrong. Okay, we put in all the data, we find the mean, we found the mean, we found the standard deviation, we found the standard error, test statistic, critical value, compared, and what was the conclusion? Failed to reject the null. The null was the average difference, not the difference, average difference. Mu is equal to 0, alternative, mu not equal to 0. If the average difference is 0 in the sense we're not rejecting the null, and the conclusion is the first measurement is consistent with the second measurement and vice versa. So, is our thermometer reliable? Yes, it consistently gives us the same answer. So now we are going to make the process a bit more simple before we get to within subjects. So, do we have the data in the calculator? Yes. once you have the differences, press start. Over to the fun part, tests. Option number 2, it says t-test. And you've got 2 options. You can either enter the data or statistics. In this problem, we have the data saved, and we also found the difference, L1 minus L2. Where did I save in my calculator? Which list? The difference. List 3. So, mu naught is whatever we have in the node, the down. I need to put in list 3 because the differences are in list 3. Good. Forget about the frequency part. The next one, we've got 3 options. Out of the 3, which one should you pick? Not equal. Very good. Who said not equal? Marcus, what made you select not equal?
Because that's the alternative.
The alternative. You look at the alternative and it is not equal to, so we pick that over, down. Does that test statistic match the one we had last time? Do we have the test statistic from last time? No, from last time. Okay, what is that? So last time. The t value that we got from the data. It's that, you know. We put it in a formula. Go ahead. I forgot your name already.
Sorry,
What's your name?
me?
Yeah.
Katie.
Kaylee, go ahead.
Is it 1.25?
It is 1.25. Very good. And look at that second line over there in the screen. What is that value? 1.2426. It is giving you the test statistic, which is more accurate, the calculator or whatever we did.
The calculator,
Obviously, the calculator. Why, Declan?
because the calculator, there's like.
Because it's the most powerful thing. One thing that could save us all. It uses 9 decimal places. It has more precision compared to our case where we rounded everything. Correct. Every time you round, you're actually going away from the exact value. Okay, so we have the test statistic. Any guesses as to what the next line is? You can look in your notes and tell me which number resembles that number. Declan,
Was the p-value?
it is the p-value. Does it matter? I used TCDF, went through that entire process, multiplied it by 2, then got to that number. But here, it is giving you the p-value. Good. The next line, what is that? What's your name? Nino. Finally he speaks. Louder, can't hear you. The mean, the sample mean. Is it the mean of temperatures or is it the mean of the difference? Sis. It is the mean of the differences, not that of the temperature. And if you have to take a guess, what is SX? Can't hear you.
Standard deviation.
Standard deviation. Good. Pretty much it does everything for you. But that is not enough, right? We can use this, but deducing and making the inference the right way is what matters. Are we clear? Good. So we are going to do a within subjects example, and we can simply use the calculator to go about making increases. Are we clear? Yes. Okay. Who wants to give me a written subject example? We have an example already, but I don't know, realistically speaking, if people would be willing to give money twice. Do you agree?
Well, I think I think the survey was like based off of their answers of their willingness to donate, so not necessarily the money.
So did their willingness increase? Okay, in that case, it will work. How will we make, should we go with that example? This is the example. We say willingness to donate money to something. Donate to ASPCA. You've seen that advertisement? No, with Sarah McLaughlin's song? Yes, okay. Before seeing the ad, oh, sorry, my bad. Not mine. So I'll make this bigger. I'm getting excited because I love that song. And ASPCA. If you don't know what I'm referring to, the name of the song is Angel by Sarah McLachlan. But they put this song, it's a very sad song. It is not about dogs or anything, it's actually about a person, close friend of hers, who died in a drug overdose. But they took that song, they put it as an ad for ASPCA. So they have this really sad looking dog, and the song is playing. So every time I see it, it has an effect. I want to donate money. So it does the job. Should we go with that, Olivia? Okay. So here is the ad. I don't want to use ASPCA. I don't want to get to. Let's just say ad for a care company or society. Good. I'm going to write a problem in a second. So people are asked to watch, people watch the ad. Last time, how many times did we measure the number of participants? 8. Let's do 7 individuals. Seven people, and we will ask them before they watch an ad as to, are you willing to donate money? Scale of 0 to 10. Only discrete values, 0, 1, 2, 3. 0 means unwilling. 10, empty my bank account. Very willing. And other values would be somewhere in between. They did a good job. That ad gets me every single time. So 7 people we record as to whether they are willing to donate or not. They watch the ad and we ask them after, did it change? But we call it within subjects because whatever I'm measuring is within one participant. If I pick the first person, I want to know what happened before the art, after the art. Subject here refers to person, it could be of an animal, it's a different setting. It's a general term. In our case, 7 people. Okay. Do we understand the scenario? Should I write it elaborately? This is good enough, right? Okay. Let's keep it simple. 7 participants. So we are going to record before and after. So 103792 3. That's before. After the art. That person is heartless. Didn't want to give money at the beginning, didn't want to give money out. In the field of psychology, whatever that goes in here it could be a treatment, it could be a drug, even in a medical setting. This part is what we call an intervention. And we want to know if the intervention had an effect or not. Okay. We want to conduct a test to determine if the intervention effect is significant. In this problem, intervention effect would simply be the effect due to the art. So that is our intervention. Good. Just like previous case, we have to define the difference first. When I started today, I said it doesn't matter whether you do L1 minus L2 or L2 minus L1 in that problem. But in this problem, what is the most reasonable thing to do? Should you do before minus after or after minus before? Sophie says after minus before. Do we agree? Yes? Yeah, Gabriel? No.
Catherine.
Wow, way off. Catherine, agree. So we want to do after minus before. Why, Catherine?
Because then it would give us the difference, like if there was an increase or a decrease, would be before or after with it.
Very good. So if things went toward the intervention, in the sense if it did have an effect, one would expect this number to move from unwilling to willing. correct? So I would expect a high bound. So a reasonable thing would be to define the difference as after minus before. Good. Could there be a scenario where one would want to do before minus after? Absolutely. There are cases where that could happen also. But depending on how you define this difference, your conclusion will change. So you've got to be careful. Let us say the assumptions hold true. I took a moment, step back, looked at the data. I wanted to be sure that this would be normal, no skews, and of course, independent people. In this case, we will violate an assumption if we chose the first two participants from the same household. Do you agree? If they live in the same house, they're probably connected somehow. One person is going to influence the other person. You are violating an assumption. Can't do this test. We're going to assume that they're all independent. Are they part? Yes. I can't measure, are you willing to spend? Ask that question to Catherine and record from Sophie after the art. Doesn't make any sense. They have to go and ask. Okay, assumptions are satisfied. We checked for assumptions, you've got to do this always, or at least know what they are. Step 2 is the definition. The rest, we can do it using the calculator. So to answer that question, that's the intervention, which in this case is the participant that we're dealing with. If it had an effect, we would expect the average difference to be your choices. You can pick, should it be greater than 0 or less than 0? If the intervention, the add, had an effect, do we expect the average difference to be bigger than 0 or less than 0? Greater than 0, do we agree? Yes. I want this number to be bigger than 0. Another way to deduce that is if you did after minus before greater than 0, use algebra, move this to the other side. You end up getting after bigger than before. So if I want to test whether after is bigger than before, this should be my setup. And over here, the average difference must be greater than 0. Good. If the alternative is greater than 0, what is the norm? Okay, so we have the data. We have defined the average difference and defined the definition of the test. Step number 3, let's pick alpha. What should we pick? Point 0.01, 0.02, 0.25, 0.1. Give me one. 0.01. If alpha is 0.01, what is the confidence level? 0.99, 1 minus that. Let's write that also. Here is my question. Is this problem any different from the previous problem in terms of the procedure that we are about to use? No. All that changed was the scenario. But in terms of the concept, what happened last time and this one, the exact same process, that's it. Why don't you give it a try and let's see if we can come up with a conclusion as to whether the ad had an effect or not. You have the data. I showed you how to do the test using the calculator. Let's see if we can come up with a conclusion. There is data. I have it entered in the calculator. What I'm going to do is do it the easier way and make connections to the formula and everything. So before is in list 1, after is in list 2. So list 1 is before, list 2 is after, so we've got to do L2 minus L1, second 2 minus second 1. Enter. It's going to put all the values in. When you enter the data, be very careful. It only takes one data point to give you the wrong conclusion. So double check always. So I have the differences saved in the third list. So all I have to do, second, start, start, over to test. Option number 2. The null value did not change because in my definition, mu is greater than 0. I just wanted to be bigger than 0, so mu sub 0 or mu naught is 0. List 3, down. Which one should I select? Greater than. Always look at the alternatives. It froze. Okay. If you select the third option and hit calculate, you can tell me the answers. Many of you had it right. So I'll have to restart this. Let's start with T. What is T?
3.74.
3.74. The P that you see up there is the P value. What is that? Before rounding. 4, 8. Let's keep 4 decimal places. Okay. X bar. Your book likes to call it M. 2. Okay. Standard deviation S. 1.414. That is 5, which is 2. Okay. N 7. I have everything that I need to get that 3.74. If you go back and look in your notes from last time, this is simply M minus mu, which is 0, divided by S over square root of N. I have the mean from the sample. So 2 over 1.414 divided that by the square root of N. and you should get 3.74. Yes.
Is M the same thing as like X bar? Is that the
Yep.
sample mean?
Yep.
Okay.
I'm using this notation because your textbook uses n.
Oh, okay.
This is for the sake of homework. In practice, we use X bar, which is why the calculator is using X bar. Are we clear? So before we get to the CDF part and inverse T, what do you think the conclusion is? The question wants to know whether the intervention effect is significant. Is it right?
Yes.
Yes. We do what?
Reject.
Reject. Okay. Why?
The p-value is less than 0.01, which is our alpha.
When in doubt, always draw this flow chart. It helps. Ask yourself this question. Is p-value less than or equal to alpha that you picked? If you say yes, you reject no. If it is no, you do not reject no. In this case, p-value is 0.0048. If decimals are confusing, convert it to a percentage. This is 0.48%. 0.48%. Alpha 0.01, that's 1%. Is 0.48% less than 1%? Yes. So flowchart says go this way, you reject no. And going back to day one, null means nothing, no effect. Alternative, you have significant effect. The inferential part is the crucial step. So I know that I have to reject the null, which implies that there is sufficient evidence to conclude a significant effect. What is this effect that we are referring to? Mu bigger than 0. Well, mu is the average difference. Difference is after minus before. Significant effect would simply mean the average values of after is bigger than the average values of before. So our conclusion is after is bigger than before. So if someone asked you, well, did the intervention, which is the add, have an effect? What would you say? Yes, because after the add, things went up, the average increased. Do keep in mind, just because the average is bigger doesn't mean that the add worked. It has to be significantly bigger. And the test concludes that it is in fact significant. So the intervention, which in this case is the add, has a significant effect on people's willingness. to donate. You see how I went from there to there? That is the most important part, especially as students of social sciences, that is the most important part. The calculator, the software can easily give you this. And that only you can do. Good. Well, you copy this. That raises up. What is that? And what I want to do now is to simply show that whatever conclusion that we already have is going to be the same, and I'll use the other approach. Which is using the cutoff. Let's see. The rejection region is on the right hand side because this is a right tail test. Why right tail? Greater than 0, 0, 0 here. What is the area, shaded area under the curve? What is that amount? 0.01. That cutoff, you either get it from the table or you get using inverse T. So in inverse T, if you put the area below and put the degrees of freedom, what number do you get?
3.14.
3.14. Today must be an irrational day. We had 1.414. It's not exactly square root of 2. That's irrational. Pi, irrational. But the it's happening. Moving on. So 3.14 is right here. Where is our test statistic? 3.74, somewhere over there. Did it fall in the rejection region?
Yes.
So if you deduce that the test statistic falls in the rejection region, you reject the null. So back to here, same conclusion. Reject the null, sufficient evidence to conclude that there is a significant effect. What effects are we studying? If the intervention worked or not. In this case, it worked. Good.
I just have a question about like the p-value. So if like I had like the problem on chapter 10 homework where it was like p is less than 0.01, then just from using the p-value, could I reject the null?
If the p-value is less than 0.01, you can't. So that is all one needs to check. Is it less than 0.01? That's exactly what I'm doing, right? All I needed is this, and I came to that conclusion. In practice, people won't even do this, but we do it so that students can connect the dots between the test statistic and the cutoff. If you get into writing articles at graduate school, that's what we go on. Good. Are we clear? One question. Let's see if you can connect this to false positives. Right over here. False positive would simply mean you are mistakenly rejecting the null. based on the evidence that you have. What is the probability, Riley? It is simply the p-value. Very good. That number is 0.0048. Going to erase all of this, I don't need it. This is the same as that, they are one and the same. I say tomato, you say tomato, we're all talking about the same thing. So the chances that I made a mistake based on the data that I observed in concluding this, which is rejecting the norm, is 0.48%. Do you think that that is a very high percentage? No, extremely small. There is a 48 in 10,000 trials or chance that I could be wrong. In other words, if I repeated this experiment 10,000 times, statistically speaking, only 48 times would I conclude something different than what I have here. The chances of a mistake is very small, so I can go ahead and comfortably reject the norm. Good? Okay. Let's see if my calculator works. Right, okay. Do we have start over to test? Yes, scroll down and you should see something called T interval. Yes, T interval, you would have the same options, data or statistics. Yes, select data. But in the list where you have the differences, which is L3, and it should ask for C level, not like C level, confidence level. 0.01 would mean we have 0.99, put in 0.99, don't put 0.01. That is level of significance. This is the confidence level. Hit enter and tell me what you get.
Point 0.83. 3.98 or 17. 3.9817.
Okay, Haley. Oh, Haley, right? Katie, did you have a question?
No, I was just gonna
Okay.
say the same answer.
You can round it to 3 decimal places. Do follow the instructions. I tend to specify on an exam. I'm sure Achieve does the same thing. Okay, so 0.0183 less than mu less than plus value. Lower bound, upper bound. Mu is the average difference. Things you cannot do. Pay close attention. That is incorrect. Can someone tell me why? All I did is change one letter. From mu, I put D. Why is it wrong?
That's just the definition
Definition of definite.
of the data set, like the average, right? Like that's how we figured it out.
No, it's not, no, you're mixing things. Riley?
Is it really what you're trying to find? It's not an actual.
That is the
According to
next
the
part, that is
definition.
the next part of
With
what
D.
you shouldn't do. But D, why is putting D there incorrect?
Are you referring to Cullen's D or
No, the
The
D from
definition.
earlier today. policy.
Because that was just one observation,
Very good,
but U is all of, like, the average of all.
very good. So one difference, but I'm not making my conclusions based on one difference. I'm using an entire sample, so it has to be the average.
So like in this, like D would mean like the difference, like would be like the difference between 1 and 4, like it would be the difference between one set of data.
Yeah.
And not like the whole average.
Whole,
Okay,
but in statistics, you've got to look at the whole
Right.
sample, not just one observation, which is why this is incorrect. This is what value was asking. Or that's what I've come to believe. Putting F, is that what you want?
I honestly forgot what I said, so.
Okay. M or X bar. You can't do that. This is also incorrect. You are not finding an interval or something you know from the sample. What is the point? Do you agree? We are trying to find that unknown difference, that is the unknown value. And the interval is for that. Not last lecture, probably the lecture before the storm. I forget. I said that you can test for something using a two-tailed test or use a confidence interval. The conclusion will be the same. If by some chance, any chance, mu equals 0 based on the data, you cannot reject the null. Good. So we have placed 99% confidence on this data. And based on that, ask yourself this: could mu equal to 0? If this is the interval and you are 99% confident that this is the interval based on the data, could mu equal 0?
Me?
Hannah, right?
Yeah.
Yeah, good.
Are you asking me to explain it?
Yeah,
Okay.
could it equal 0?
No, I don't.
No, it can't equal 0 because the lowest value is 0.1. But 0 doesn't fall here. So you are 99% confident that 0 is not a possible value, which means it's definitely bigger than 0. All the values are bigger than 0. Good. Great question. What about the 1% that you're not confident? Well, you are never 100% certain. It is only possible at a level of 1%. It is possible, but the level of 1%, which is why we combine this with the p-value conclusion. The chances that I would make a mistake would have made a mistake in concluding that I reject the null is 0.48%. Small. I get an interval 0 doesn't fall based on 99% confidence. Put those two together, you know that, I have good amount of evidence to support that statement. Good. When you do a test, the conclusion that you get from the confidence interval shouldn't, will not, mustn't differ from the conclusion that you get from the p-value and the conclusion that you get from the critical value. They're all talking about the same thing. Interpretation-wise, things are different. Conclusion-wise, they're all the same. Good.